a special type of binary tree that we call binary search tree, or BSD, and it's also an abstract data type. We're going to be examining the definition of a BSD and also some other aspects relating to a BSD. So first let's define a BSD. BSD, of course, is a binary tree. So this tells us a lot about it. So it's a tree and it's binary. The number of children, the maximum number of children of a node is 2. Then there are these extra definition elements that we've added to the binary search tree. First of all the elements in the tree, or all the nodes, we also call them keys. So the elements that are contained in a node are actually called keys in a binary search tree, are comparable. So it does make sense to compare the elements contained in that binary search tree. It must make sense. If it doesn't, then it doesn't qualify as a BSD. So if we're talking about digits, then it does make sense to compare them. We can compare 1 to 2 and say 1 is less than 2, and 1 to 3, and so on and so forth. If we're talking about letters in the alphabet, it also makes sense to compare them because some letters come before others. So if you're going to define your own class, you're going to have to make sure that, and you want to use it in a BST, the objects of that class, then you have to make sure that they are comparable. All the elements in the tree, all the keys, are unique. We cannot have two same elements in the same tree. And finally, and this is one of the important properties of a BSD, is that for every node in a tree, and since we said that all the elements in the nodes can be compared, all the nodes to the left of that particular node that we're looking at have elements that are smaller than 1, or that particular node. In this case it's 1. And all the elements to the right will have a value or a key that is larger than the parent node. And this is a very important property of BSDs because it will actually allow us to, we can just scan through our tree going from left to right, and we will get the elements of the tree in their proper order. And this is why they call BSDs. There's a search element to it. If you remember binary search, when we looked at a linear way of applying a binary search algorithm, then we were making use or exploiting the fact that a tree was, or a list was sorted, and this allowed us to divide the list in halves and keep on looking for an element. So for example, if this was our tree, and this is actually a binary search tree because as you can see, suppose we looked at D. All the elements to the left are actually less than D. A, B, C comes before D. And all the elements to the right are greater than D. E comes after D. And same for B here. One important property of a BSD is that if you performed an in-order traversal, just like I mentioned, of the tree, you will get all the elements in their proper order. So if we actually performed an in-order traversal, we would traverse them as a depth first. So we would go all the way down, then reach A, and then we go to, it's an in order, so it's left child, parent, right child, A, B, C, and then parent, D, and then finally right child, so A, B, C, D, E. So you get them in their proper order. For a given set of elements, we could actually represent binary search trees for them in multiple ways, and there are multiple possibilities of creating binary search trees for a given set. So if we had, for example, 1, 2, 3, we could put 1 here, okay, and 2 and 3, right? This would qualify as a binary search tree. 2 is larger than 1, so it comes to its right. 3 is larger than 2, and so it comes to its right. And you could also put 2 here and have 1 and 3. So this is another representation of the same data set. So how many such possibilities can we find for a given set of elements? The way to do that is to use a recurrence relationship. So if you define T of n, where n is the number of elements we have in that set, as a number of possible binary search trees we could create, and if we identified every single node as we gave it an index from 1 to n, then node I, if we looked at a particular node here, well, basically what's going to give us all the multiple representations of the binary search trees for a given set is by taking every single node and assigning it at the top of our tree as the root of our tree. So here we've assigned 1 as the root, and then here we've assigned 2. And then doing this in a recursive fashion. So if we looked at node I here, and we were going to have I minus 1 elements smaller and n minus